Our task is to determine the plant population density which will optimise the yield of a crop from a given area of land. In order to do so, we must produce a mathematical model which gives the yield of a crop as a function of time throughout its growth, then explore the effect on this function of varying the number of crops planted per unit area. Our aim for producing a mathematical model is to examine the growth rate. So long as there are sufficient resources, there should be a positive growth rate, up until the point where the crops run out of nutrients, space, sunlight, water, or other resources, which will cause the growth rate to slow down. Having modelled the growth rate, we will derive a function for yield in terms of time. The model must then be related to experimental data in order to draw conclusions about the best time to harvest the crops and the optimal plant population density. These assumptions are based on the conditions used to run the experiments in the Aspinall and Milthorpe paper. Our final assumption is that the conditions, such as water level and light intensity, are such that the plants can grow healthily. When a crop is planted, due to there being limited resources, we are assuming the plants grow to some maximum mass. Even if a plant was given unlimited time to grow, it would never exceed their limit. The graph of mass of the crop over time tends towards an asymptote of maximum mass. Yield per unit area is the total mass of all collected material from that area if harvested at any single time. Yield equals the mass per crop multiplied by the number of crops per unit area. As long as there are enough resources available, each plant will continue growing to its maximum potential mass. We would expect yield to demonstrate similar behaviour to mass, just scaled by a factor of n. However, in reality there will be limited resources and multiple plants fighting over these resources. This means that the maximum mass for each plant in that area is no longer the maximum mass of one individual plant growing without competition. Limited space for growth of roots and limited resources means that plants can't reach their limit. Planting more crops in a given area reduces the maximum mass that each plant can reach, thus the yield tends to a maximum yield, Y max. The yield follows a simple logistics model. Using separation of variables will enable us to solve this differential equation. First, however, we must use partial fractions to rewrite the right-hand side before it can be rearranged. Both sides are then integrated as shown, using the initial set of conditions, i.e. that when t equals 0, y equals initial yield per unit area, denoted by y subscript 0, we calculate the value of c, from which an expression for e to the power minus c can be derived. Given this, the expression for e to the power kt plus c can be rearranged. As demonstrated, this eventually gives a formula for the yield per unit area in terms of time. The graph is steeper for higher values of k. This is because the rate of growth equals ky multiplied by 1 minus y over y max, so a higher k results in a faster rate of growth. For a higher initial yield, the graph has both a higher starting point and a faster initial rate of change of yield. Initial yield is equal to the number of plants multiplied by mass per plant, so a higher plant population density gives a higher starting point and a faster rate of change. When the initial number of plants increases, the rate of change of yield increases. However, a larger initial number of plants gives a larger population density, for which the growth pattern is given by a lower value of k, hence the rate of change of yield is lower. Since increasing the population density results in both an increase and decrease in the rate of change, the graph tends to the same limit for different population densities. We can validate this by looking at our data. As you can see, a higher population density fits the model with a lower value of k, showing that k decreases as the competition between plants increases. Each plant will require a certain size space of land to grow without competition. In a large plot of land, many plants can grow undisturbed, so long as the spacing between plants is large enough. We would expect these to grow according to our first model, which looks into plants growing without competition. Although this technique allows plants to consistently grow to as large as possible, there is space and other resources that are not being used, so are going to waste. This means the yield will not reach as large as it could do with the resources available. From our data, we observe that with 4 and 8 plants per plot, there is a significantly lower yield compared to 16 to 128 plants per plot, since at these lower population densities they are not yet completely using up all the resources available, so the yield will not become as large. As 16 plants per plot is surpassed, the yield, as predicted by our model, always tends to a maximum yield of around 60 grams per plot. This is due to the limited resources. Because it does not make much difference using 16 plants per plot compared to 128 plants per plot, to maximise profit from each batch we would advise a density at the lower end of this range. This means that, for very little yield difference, less money will initially be spent buying the seeds, and time will also be saved if less seeds have to be planted. In reality, many seeds will fail to germinate or will die at a very early stage. Research suggests that only 85% of seeds germinate, so to ensure that all resources are used up, we suggest a population density of around 30 seeds per plot, as this ensures the amount of plants per plot stays above this threshold of 16 without having unnecessarily large amounts of seeds planted for little effect. Looking at population density of 16 plants and over, as mentioned before, the yield tends towards a value of around 60 grams. After 6 weeks, all these points are within 30% of this maximum, and after 7 weeks the yield looks as though it will be within 20% of this. Leaving the barley to grow after this point will not return much additional growth, but risks plants dying or being destroyed. Therefore, it is best to harvest the barley between 6 and 7 weeks after sowing. Our research suggests that barley is typically harvested after 40 to 55 days, which validates our results. Given a 10-inch circular plot, we would suggest between 16 and 32 plants per plot as the optimum population density. Since plants are not guaranteed to survive early life, we suggest that around 30 seeds should be planted. This gives a density of 30 plants per 0.05 square metres, which equates to 600 plants per square metre. These results appear plausible, as each barley plant would take up a 4 cm by 4 cm square.